Welcome to Lecture Online, and now we're going to try and find the field caused, or the electric field caused by a ring of charge. So here we have a circular ring. The radius is x. It has a certain amount of charge on it. So let's say that the Q of charge was added to the ring. And so therefore the linear charge density on the ring is going to be the total charge divided by the total length of the ring, which is going to be Q divided by 2 pi x, x serving here as the radius of the ring, not to be confused by the distance from the point where I want to find the strength of the electric field to any point along the ring. We'll call that large R. So therefore I used x for the radius of the circle. And A is the distance from the point of interest to the center of the circle. This point will be centered directly above this point right there. And so therefore we have a nice geometry between x, the radius, A, the distance to the point, and then R will be the hypotenuse, which would therefore be equal to the square root of x squared plus a squared. All right, now, if I take a small little segment right there and say that little segment will contain a certain amount of dq on it, right there, and of course then we'll have an electric field right here in this direction caused by the small amount of dq, and therefore the electric field will be equal to dE. It's not a very good looking D, so let me try it again. That would be dE. That would be the strength of the electric field in this direction caused by the small little dq. Now, this is a small little length on the circle right there, so we can call the length here equal to a ds. And then if we think about that, we can say that this subtends a small little angle. We'll call this angle right here d phi, and therefore we can write that ds is equal to the radius, which is x times d phi. And then we can see that ds can be related to dq as follows. We can say that dq is equal to the linear charge density lambda times the small little length of that segment ds, which of course is x d phi. All right, so that's the charge that causes the electric field right here, dE. Now notice that we're going to then sum up all those little line segments all the way around the circle, and they will cause all the little dE's. Of course, remember that dE will then kind of go around like this. But if you think about it, in each case, dE will have a component which is horizontal, and will have a component which is radially outward away from this point. So in this case, it'll be straight down, but if I pick a point over here, that component will be this way. If I pick a point here, the component will be this way. If I pick a component over here, it'll be this way. So you can see that in the end, if I add up all the little line segments right here, these components right here of all the dE's will cancel each other out. And the only one I have to worry about is this component right there. So these components will simply cancel out, which means I only need to find the sum of all the dEx's. And then you can see that we have this angle right here, called this angle theta, and I can say that dEx is equal to dE times the cosine of theta. Okay, now what we have to find is what is the magnitude of dE and what is the equivalent for the cosine of theta. Well, the magnitude of dE is going to be equal to k, the constant k, times the charge that causes the electric field divided by the distance squared from the point where I want to find the electric field to the charge that's causing that electric field. And since R is equal to this, and if I square it, I get x squared plus a squared, I can say that this is equal to k times dq. Now dq is equal to the linear density times ds divided by r squared, which is going to be x squared plus a squared. I can also find what the cosine of theta is equal to. The cosine of theta, by definition, is equal to the adjacent side. Sometimes I get ahead of myself. It's equal to the adjacent side divided by the hypotenuse. In this case, the adjacent side, now notice, if I'm talking about this angle right here, theta, that's the same as this angle theta right there. And that means the adjacent side is A, and the hypotenuse is R. So it'd be A over R, so it would be equal to A divided by the square root of x squared plus a squared. And then, if I want to find the dEx, only the x component of the small amount of dE, I simply multiplied dE times the cosine of theta. dE is equal to this, so it would be k times lambda times ds divided by x squared plus a squared. And multiply that times the cosine of theta, which is equal to a divided by the square root of x squared plus a squared. If I multiply that together, I get the following. I get dEx. That means the horizontal component of the electric field at this location caused by a small little line segment is going to be equal to k lambda ds. Oh, don't forget the a. Let me throw the a in there. A times ds divided by the quantity x squared plus a squared to the 3/2 power. Now, if I want to find the total electric field, I need to sum all of those line segments together. But notice that for each little line segment, the magnitude of dx will remain constant. And also notice that x will remain constant because that's the radius of the circle, and a will remain constant. So in this case, a and x are both constants. The only thing that varies is the angle phi or the line segment ds. So we'll get to that in just a moment. So now what we want to do is we want to sum them all up. So we can say that E in the x direction, which is the total E, is equal to the sum of all the little dEx's, which is equal to the sum of all the k lambda a ds divided by x squared plus a squared to the 3/2 power. And that's not a very good looking 3. Get a little lazy sometimes. So 3/2 power. There we go. Now, what are we integrating? Well, we're integrating all the way around the circle. ds, I sum them all up. So what is the integral of ds all the way around the circle? Well, it's simply the circumference of the circle. So we can actually make this pretty simple. We could say that this is equal to k lambda a, those are all constants, divided by x squared plus a squared to the 3/2 power. That's all a constant times the integral ds. Now, we're going to integrate from the beginning of the circle all the way around. So we can say that's equal to from 0 to 2 pi x. Let's see, actually, pretty easy integral, isn't it? We could have also converted to x times d theta and then integrate, or d phi, and then integrate around d phi from 0 to 2 pi. Same thing, we get the exact same result. So if we do that, so this is equal to k lambda a divided by x squared plus a squared to the 3/2 power, and that would be s evaluated from 0 to 2 pi x. Just to go through the motion, because I think we know what the answer is here, so we really didn't need to do that. So plug in the upper limit, we get 2 pi x, plug in the lower limit, we get 0. So this is equal to k lambda a 2 pi x divided by x squared plus a squared to the 3/2 power. Okay, want to simplify that a little bit? Probably do. So this is the magnitude. If you want to turn it into a vector, we'll put an arrow on there and move the directional vector there, the unit vector on the right. But notice that k, the constant, is equal to 1 over 4 pi epsilon sub naught. And so sometimes what we like to do is we like to go ahead and replace k by 4 pi epsilon sub naught so we can get rid of the 2 and the pi. And if we do that, we can say this is equal to 1 over 4 pi epsilon sub naught times lambda a 2 pi x and divide by x squared plus a squared to the 3/2 power. And then you can see that the pi cancels out, and this 2 and that 4 cancels out to that. And then in the end, you could write it as E is equal to lambda a, the 2 is gone, we have an x divided by 2 epsilon sub naught times the quantity x squared plus a squared to the 3/2 power. And then sometimes we can still make a change. We can also replace the lambda by q over L, which is q divided by 2 pi x, if the total charge on the ring is known, and then we can write in terms of the total charge on the ring. And then if we do that, we didn't have to make this conversion from k to 1 over 4 pi epsilon sub naught. If we had replaced lambda by q divided by 2 pi x, the 2 pi x's would have canceled out. And I'm kind of running out of room here, so I'm going to take this whole thing and move it over there. We could have also written it as E is equal to, so we're going to replace lambda over here by q over L, or q divided by 2 pi x, and then the 2 pi x's would cancel out, so then all we would left is q, so that would be k q times a divided by, and we'd keep this whole thing right here as x squared plus a squared to the 3/2 power. So that would be another way in which we can write it. So these are different forms of the very same answer, depending upon what you feel most comfortable with. Now, one more thing we'd like to consider here is notice that in this particular case, the way this is drawn, the location A is relatively small to the radius of the circle. And so that is an appropriate answer. But what would it become when A became really big? What would that answer become when A becomes much, much bigger than x? Well, if A becomes much, much bigger than x, then x can be ignored. A will then become very large, and then a to the 2nd power raised to the 3/2 power becomes a to the 3rd power, and then a divided by a to the 3rd power, that becomes a to the 2nd power in the denominator. So this is approximately equal to kq divided by a squared for the condition where a is much, much larger than x. And notice then this whole ring of charge then becomes like a point object with a single charge on it. So it becomes like a point charge because A is so far away, the ring acts like it's a single charge directly away, a distance A away from the point of interest. So that gives us a lot of confidence that this answer is correct because it does come back down to the standard answer for A being a very large distance. But for short distances, what we have boxed there are your typical answers for the electric field strength at a distance A away from a ring full of charge.